Dear students, in this video we are going to discuss about the experiment number 9 and 10. Both are same only, except in experiment 10 we are going to use one neural network instead of a PI controller. Okay. So what is hybrid? Here the title is simulation study of hybrid power system. Okay. What do you mean by hybrid? Hybrid means uh, two or more different sources we are going to, if you are going to connect, then we call it as a hybrid system. Okay, so currently this is a grid connected system, so that's why I have not included any battery. In case if you are going to use any if you're trying to design a standalone system, then battery is required for the uninterrupted power supply. Okay, uninterrupted power supply. Fine. Now in last videos we have discussed individually we try to execute this simulation by using wind energy and PV power. Okay, here we try to combine both the things. Okay, almost same simulation files I have used. Okay, I have not changed anything except that here I have used a three level, since in earlier stages we have used only single phase. Here we are introducing the three phase. Okay, so in inverter video, I have already designed how to design an inverter for the three phase. You can check those videos, okay, for the inverter design. And this is the basic wind model, okay. This already we have discussed in the previous videos, and this is its MPPT. And this is about the solar PV. Okay, here we are going to change the irradiation and temperature. And this is our boost converter, and we are going to use a MPPT technique, and here we are going to calculate the power, and we are going to use a tag to calculate to measure the power. Okay, so this blocks already we have discussed, so I am not discussing again it. So this block we have to discuss. So earlier case we have used only single phase. I have taken only single one. Okay, here we are going to take the three phase. So three sources I have taken in a star combination, and I have connected it to the neutral, and each voltage I try to calculate. Okay, each phase voltage. Actually, these are phase voltages, not line voltages. Kindly note that all these are phase voltage. That is, from this is a phase voltage, and then the another one is a neutral. Okay, so this is a phase voltage VANM, VBNM, VCNM. Okay, and then now we need three vectors, right? Three unit vectors for each phase. So divided by maximum value. Okay, this is a divided by maximum value. Then we are going to obtain. Oh, okay, we'll go to the MATLAB file directly. So this is my source. So these are my values. Okay, 1A 1 by VAP. VAP is a maximum value. Here I have masked the data. Okay, fine. These are the three unit vectors, and then I try to calculate the RMS value also. Okay, fine. After this one, this is my three-phase inverter. How to design this inverter and all already we have discussed. Please go through the previous videos. And this is our control loop. So here in the control loop, I try to maintain a voltage of 800 volts. This is the estimation. Currently I have not done the estimation here. Okay, if you want you can do it, you can include it. At the end we will see it. Okay, so this is a 800 voltage. What is this 800 voltage? This is a DC link voltage. Which voltage this is? Actually the input to the inverter. Okay, that is here, this voltage. This is my uh, inverter. Okay, to this inverter, whatever may be the voltage is there, that is the DC link voltage. Okay, this DC link voltage I want to maintain it as constant. Okay, so this is the DC voltage, VDC voltage. Okay, so this DC voltage I am going to compare it with the 800 volts. This is the reference value. Whatever may be the PA value I am going to get, this I am considering it as a current reference, and since it is a DC component, I am converting it into the AC. Okay, for A phase, for B phase, for C phase. Then I am going to compare it to the actual one, and then I am going to process it into the P controller. Okay, basically there is a P controller. Okay, here I have masked all these KPK values and all. Okay, so again we are going to do the normalization process. This is nothing but your normalization process, and then finally we are going to get the VCon. What is this normalization process? You can check in the earlier videos. Okay, and there I have explained, and how to estimate the power also I have explained there. Okay, so here it is not required, or else keep it. So here we'll connect like this, then we'll try to estimate it like this. Okay, that's it, and we'll try to run it. I'm not sure. Okay, estimation is not working properly currently. Okay, try to remove that estimation. So window model is already we have discussed. This is MPPT model. Then this is three-phase grid model. Okay, it's a grid model. Then this is our inverter. This is the inverter, and then this is a PV module. Okay, here we are changing the irradiation and temperature. Okay, here how I have changed here is, you can see here at a time 2 seconds. Okay, initially its value is 1000. After 2 seconds it will be 600 volts. Okay, here after 4 seconds, and initial value is 25 degrees Celsius. After 4 seconds it is coming around 40. Okay, then here in wind I have given a speed. Okay, different speeds I have given. At 2 seconds it is from 16 to 14 meters per second wind speed actually. Okay, at 3 it is 12, and at 4 it is 10. Okay, like that I have given. Okay, here at the end these are my measurements log. This one we have not discussed. Switching frequency, this already we have discussed it in the inverter case. Okay, here we have taken sine signals, if you remember. So instead of those sine signals, now we can use a VCon A, VCon B, VCon C, which we have obtained from the control block. Okay, right? Control block, VCon A, VCon B, VCon C. Right. So this is about the measurement. Okay. Instead of this one, here itself I will try to measure. Okay, here speed is there. Power we have to measure, right? So we'll take the power of PV. Okay. This is our PV power. Sorry, something else has come. PV power and then wind power. To use one adder. This will give the sum of the power. And then we need to calculate the current also. Okay, try to use current IA, then IB, Nice. Sometimes if you don't find this tax image, just update it. Okay, here update the tax, then it will update. Then it will show current, and then DC link voltage. Okay, I will take the DC link voltage here. We cannot exactly take all this data at a time. Okay, so we'll try to do like this itself. Okay, and I will take a mux block here. How many inputs? Three inputs, right? Three inputs. Okay, so again, select this three tags, press Control and press on this one. Okay, like this you can directly, need not required to connect manually every time. Okay, so this is sufficient currently. This results again we will see it here instead of here. We'll take separate. One is sorry, speed, then irradiation, right? We are not taking anything irradiation tags here. Okay, we'll take this tag. This is IRR, right? Okay, this is temp. Sometimes you may not give this is as global. Okay, so try to remember that we have to change its visibility to global. Okay, these are things are just for your calculations. Okay, sometimes you will be asked what is the speed, corresponding speed, how the power is going to vary. Okay, all these things sometimes they may ask you, so that's why I'm giving all these things. Okay, and again the same thing, current. Okay, sir, every time why we are highlighting current, because through current only we can able to understand that whether power injecting or not. Okay, so how many? 1 2 3 4 and 5. Okay, including the currents. 1 2 3 4 5. Okay, 5 displays. Okay, here PV power, wind power, and combination of PV and powers, and then this currents. Okay, now we'll make it only 4. 4 is sufficient for us. Apply. Okay, and then change the layout. Which way we'll do like this, huh? Okay, so this is our module. Okay, now I will try to run it. Here I think already we have given this values. Might be I might have given. I have not logged the data anywhere else. I have done it. Okay, I have not logged the data, it seems. I'll try to log the data. Okay, try to log the data. This will help us to V and I. Okay, I will give the name like this. again we have to run, okay, because we have not saved any data, right? So that's why we have to keep. You can see here why we need to take this waveform is we have to check whether these are in phase or not. Okay, it may look like they are out of phase for you because I have not given negative here, so I will give you a negative here. Otherwise you may think it's not in phase because power flowing from source to load, we are, if you take it as positive, then the converse is negative only, right? This converse is negative. Or you can see here, in other words, here power will flow from here to here, right? Here to grid. So, but I have connected it here positive and here negative. So that's why I'm taking here as negative. Okay. Again, I will try to run it. So here you can observe this is your basic table. Okay, I will try to change these things. Okay, here output power, output power. I will do one calculation. Remaining you can do it. Okay, watts and efficiency. Okay, fine. Now we'll check each and every result. Okay, here you can see that this is in phase. You can check here this voltage and current is in phase with the voltage. So it means power factor is almost unity. Okay, this is over. Next thing is speed against the speed. Okay, this is a wind speed. Actually, I have to include the irradiation also. Instead, you can check here. For that, I will try to check here the VDC. Okay, here we have observed, we have applied a change, right, at 2 seconds, 3 seconds, 4 seconds. So that's why it a little bit variation you can able to observe in the DC link voltage. This is your DC link voltage. Okay, so here DC variation is also very less. Okay, it is less than 2.5%. That is this ripple. Okay, and this has to overcome in 2 seconds. Okay, it is less than 2 seconds it is taking, so it's fine. It is taking only 0.2 seconds. Okay, the dynamic you can observe here, the dynamic it is clearing in 0.2 seconds. Okay, you can say the system is working perfectly, not exactly perfectly, it's okay, or it is minimum standards it is maintaining. Okay, so this is a DC link voltage, this is the current. Fine, now we'll see the data. Okay, speed. Okay, so this is a wind speed, and then this is a irradiation. Okay, and then this is a temperature, uh, and then this is a VDC voltage. Okay, the VDC is constant every time. For the change in these things, we can observe clearly the current change. Okay, current change. Here, okay, for every change, you can observe the current. Injected current is affecting. Okay, fine. Whether these currents are, okay, here we'll observe it. Okay, this is your power. This is PV power, and then the wind power. It is a combination of these two powers, and then this is a power. this is your current. Okay, you can check here, all these currents are exactly out of phase, and there is no offset. Okay, there is no offset here. Whatever may be the voltage is the same is reflecting here also. Okay, and they all currents are balanced. You can observe these are balanced currents. Okay, now we'll try to check the THD. Okay, go to THD, and apart from the THD, we can able to observe the, here we will get all the signals actually. Okay, so this is our current signal, and see here, suppose I want to calculate the current here and the 50 ounces, then you have to choose the steady state. Here I can take starting time as 1. Okay, number of cycles you can take up to 5 cycles. Okay, then what is the fundamental frequency? 50 Hz, right? How much frequency I want to calculate? Okay, I mean display. Okay, then display. So here I can check that 2.65% is my THD and 32.61 is my current. This is the maximum current. Okay, this is the maximum current. Now we'll try to check the data. Okay, what is the window speed here? That is 16. You can check here. So here at initially I have given the speed. Initially I have given the speed 16. Okay, you can observe here. So this is a 16. Okay, then generated power here is whatever the power generated here is, from this one you can get. Okay, here power is almost, see I am taking the near values. Okay, near values, that is 1.44 into 10 power 4. Okay, 1 2 3 4 14400. Okay, now irradiation is 1000. Okay, so how do you refer, sir? You can refer from here. Okay, so here the irradiation is 1000. Okay, so what is the power? Or because almost 2 point, earlier we have taken 2.6, right? So 2600. Okay, current injected, how much it is the current injected? Or you can check here from the THD. From the THD we can observe that it is 32.61. Okay, 32.61. 32.61 divided by, because this is a maximum value. Okay, 1.414. Then this is 23.06. Okay, this is 23.06. Okay, now I have to calculate the output power. How to calculate the output power? So again we are going to apply the formula, right? 3 VA cos phi, right? This is the phase current, and then we are going to calculate the voltage. Okay, that is into 1.732 into 415. See, this is connected to the grid. Our grid voltage and will not change. Okay, that is 415, fixed one, and cos theta is 1, right? So it is coming around 16576. Okay, now we'll try to calculate the efficiency. Okay, divided by 14400 plus 2600. It is coming around 97.5%. Okay, 97.5%. Okay, now what I have done, this is our wind speed. What is the wind power generated? That is 14.4 kilowatt. And then in radiation is 1000. How much power is generating? That is 2600. And how much current is injecting? This we can able to calculate through the FFT analysis. Okay. And then this is your output power. Okay, sir, suppose now at this condition, what is how to find out? So here it is steady state we are going to get here. Please don't take here, here, here like that. Okay, you take here 2.5. At this 2.5, what is the wind speed? What is the generator speed? Irradiation, how much? Sir, how to get the wind speed, sir? You can check here the wind speed. Okay, your wind speed will be like this. Okay, up to from 0 to 2 it is 16. After 2 it is changed to 14. So after 2 to 3 you are going to get 14. Again 3 to 4 it is 12. After 4 it will be 10. Clear? Then similarly here also irradiation. So starting it is 1000. After 2 seconds it will be 600 and it will be 600 only after that. Here temperature initially it is 25 degrees up to 4 seconds. After 4 seconds it is going to change to the 40 up to infinity, whatever may be. Okay, right. This is hope now you have understood how to calculate these things. Okay, now one calculation also I have shown you. Okay, okay, sir, what about experiment 10? Experiment 10 is basically changing this PA controller. Here earlier we have used PA controller, right? Instead of PA controller, we are going to introduce a neural networks. Currently it is not properly tuned. Okay, it is not exactly giving the values. Again, we have to tune it. Anyways, procedure is same. Procedure is same procedure. That is, what are the measurements we have done here in the experiment number 9. Okay, this thing will remain same. Okay, only change is in this control block. Instead of PA controller, we are using a neural networks. Okay, check here. So the currents are stabilizing. Due to some error, it has happened. So VDC will check. It is actually, it is not getting constant here at 800. It has to stabilize, but it is not stabilizing. We need a proper tuning actually. So no issue. So this is about the experiment number 9 and experiment number 10. Hope I have clarified all your doubts.